Hello dear students, welcome to Pen and Paper Chemistry on YouTube. So are you all ready with your pen and notebook? Because we are going to continue with the topic of alcohols and we are taking up some of the remaining reactions today. Let us see how many we are able to do today. So we're going to talk about dehydration and specifically the dehydration of alcohols and nucleophilic substitution, special example of ethanol getting converted into ether. It's a very, very important reaction and sometimes gets confusing also because of the reaction conditions. So don't forget to note down what we are going to learn today. We are going to study the dehydration of alcohols under the category reactions of alkyl and the OH group. So dehydration of alcohols, as you can see, can be brought about by a number of reagents. So we've got concentrated H2SO4 at 443 Kelvin, phosphoric acid, of course, by heating, anhydrous zinc chloride, alumina, at 623 Kelvin. But interestingly, we notice that as we move from primary to secondary to tertiary alcohols, notice the reaction conditions. They are becoming more and more lenient. That means we can carry out the dehydration of a secondary alcohol at a lower temperature as compared to how we can do for a primary alcohol. Similarly, for a tertiary alcohol, you will notice that we just need a temperature of around 25 degrees Celsius with concentrated H2SO4 to remove the H2O molecule. Same way when we are using phosphoric acid. So here we've got phosphoric acid and heat, we've got 85% phosphoric acid, we've got just 20% phosphoric acid. So what does this tell you about the ease with which dehydration can take place in the case of alcohols? This is your observation. Don't memorize things. Look at the reaction conditions. So here it's strongly, kind of very pure H3PO4 phosphoric acid, 85%, and here it's just 20%. Yes, of course, the tertiary alcohols undergo dehydration faster and more easily as compared to secondary, which in turn happens easier than a primary. So we say the ease of dehydration is tertiary greater than secondary greater than primary. And as we've done under the basics of organic chemistry, we notice that in the case of tertiary and secondary alcohols, the mechanism followed would be a unimolecular elimination reaction, whereas for 1 degree alcohol, it's a bimolecular elimination. Now, the important thing, yes, to complete the reaction. So let's get started. We just have to remove a water molecule. Now when we remove a water molecule, what we are going to do is C, H, H, CH3, CH2, OH. Now here it's an example of beta elimination. What is beta elimination? Wherein the removal of hydrogen takes place from the beta carbon. Again, I'm giving you too many terms, right? The carbon to which the OH group is attached is alpha carbon. The carbon next to it is beta carbon. You can also number them as 1 and 2. So this would be an example of 1,2 elimination. Okay, just for this example. More appropriately, beta elimination. So OH goes off from this carbon, right? The hydrogen, on the other hand, goes out from the carbon adjacent to it. Yeah, we have to leave out the carbon. We just remove the hydrogen from this. And they will combine to form water. Now, look at the carbon. its valency is not satisfied. It's got 3 bonds here, it's got 3 bonds here. So the 2 carbon, what do? They tell each other, okay, now let's make friends with each other, right? We don't have an option. With the result, it gets converted into alkene. There's a double bond between the 2 carbon atoms, and this gives us an alkene. So this is an example of beta elimination, wherein the hydrogen is removed from a carbon adjacent to the carbon carrying the OH group. Although we have discussed this earlier as well. Now go ahead and try writing the products of the reactions that you see on your screen. And everywhere, please make sure that you write the reaction conditions. More you write, more you will remember. That's why the name of the channel, Pen and Paper Chemistry. Okay, so the first one has been done for you. Go ahead, next one. Now, many a times, we notice that the student will remove this OH, and what the students do is they remove this OH. Is it correct? Look at what we did earlier. We said that it is an example of beta elimination. So the OH and H move out from adjacent carbon, not from the same carbon. If it goes out from the same carbon, then that's an example of alpha elimination. We are not talking about that. We are going to remove the OH and the hydrogen from adjacent carbon. So you remove the OH, right, from one carbon, but you remove the H from the carbon atom which is next to it. So what we can do is we can take off the hydrogen from one of this. Because here both the methyl groups are equivalent, right? So what do? We remove a hydrogen from the beta carbon. There we go. And we remove the OH group. Now what will happen? The 2 carbon atoms will form a double bond with each other. So what will be the product formed? Yes. So did you manage to get the product? We'll get, what is the name of this product? Yes, this is propene. By the way, in this video, I am taking up very, very simple examples, not the complex ones where a rearrangement takes place. So please don't take tension if you don't see those examples here. Okay, now try the next one yourself. You see there are 3 alkyl groups and they are all in the equivalent position. So you can either remove a hydrogen from here or here or here. Go ahead, write the product. Okay, let's tally our answer. Did you get the product here? What is the IUPAC name of this compound? Name this compound according to the IUPAC system. So 1, 2 and 3. So we will have 2-methyl prop 2-ene or 1-ene. Yes, it will be 1-ene because the double bond is between carbon number 1 and 2. So we usually don't state position number 1. So this is 2-methyl propene. So these are all examples of dehydration reactions. Now here's a question for you over here. I've given you an alcohol and you have to carry out its dehydration. What will be the product of dehydration? Remember, OH and H will not go out from the same carbon atom. Try drawing the products. Go ahead. Yes. It is good to try it out yourself. Yes, you may get 2 products. Yes, don't worry. 2 products are possible. Good. So I can have the hydrogen being removed from the first carbon, that is the methyl group. So CH2 double bond, CH, CH2, CH3. Or the possibility is that the hydrogen could be released from the carbon next to it. So we've got here the second possibility of the product is CH3, CH, double bond, CH, CH3. Did you write both the products? Now what has been observed is that when we actually practically carry out this reaction, first of all, let's name these products. So we'll have 1, 2, 3, 4. So the name of this product is butene, whereas the second one, 1, 2, 3, 4. So this would be but-2-ene, right? Because the double bond is between position number 2 and 3, correct? Our but-2-ene, which is a more substituted product, will be our major product over here, whereas butene would be the minor product. Now this was beautifully observed by a Russian scientist, after whom we've named what we call as the Zaitsev rule or the Zaitsev rule, which states that when elimination takes place, the alkene formed will preferentially be the one which has higher number of alkyl groups. Now what do I mean by this? That means the more substituted. Now let's write the structure of this alkene first. Then you'll understand what I mean by more number of alkyl groups. So this is our alkene, right? My CH2, CH3 is one alkyl group. Look at the double bonded carbon and look at the number of alkyl groups attached to it. So it's got only one alkyl groups, the others are hydrogen. Let's draw the expanded structure of the second. So C double bond. See, you can try it out yourself as well. It's good. You will learn it better. H, CH3, right? Or you could write it the other way around also. So you'll have CH and CH3. Doesn't make a difference. Why? Because I'm not talking about geometrical isomerism over here. Now look at the structures. Here the doubly bonded carbon atoms have one alkyl group and a second alkyl group. We are not talking about the size. We are talking about the number of alkyl groups. So here there are more alkyl groups. More alkyl groups means this is more substituted. So something which is an alkene which is more substituted will be preferred, will be the major product compared to one which is less substituted, and we call it as the Zaitsev rule. Now when we were writing these reactions, you would have seen a little thing written in red over here which says very important to maintain the temperature of the reaction mixture, especially when you are using concentrated H2SO4 or alumina. Remember the temperature conditions, 170 degrees Celsius or 350 degrees Celsius now. So if you are dealing with degrees Celsius, you can convert the temperatures in Kelvin to Celsius. Why is it important to maintain the temperature during this reaction? Let's understand that. Look at this chart. It very clearly indicates to you what happens if the temperature changes. So let's take the example of concentrated H2SO4. So when I was carrying out the reaction at 140 degrees Celsius, yes, I changed the temperature to Celsius. Convert it into Kelvin. How do you do it? How do you convert temperature into Kelvin? 140 plus 273. Simple, right? Okay. So something should be there, right, to keep you engaged. So what happens here is, when you carry out the reaction with concentrated H2SO4 at 140 degrees Celsius, we notice that instead of undergoing a dehydration, Our alcohol actually undergoes nucleophilic substitution reaction, and here we are specifically taking the example of ethanol. So this forms ether instead of alkene. Similarly, if you're taking Al2O3 alumina, 473 Kelvin, right? You get an ether as the product. But if you increase the temperature, you'll get the eliminated product. That means where water has been released. Similarly, concentrated H2SO4 at 170 degrees Celsius gives you an elimination product, whereas 140 degrees Celsius gives you an ether by bimolecular nucleophilic substitution reaction, what we call as an SN2 reaction. Oh, it is confusing, right? So we want to understand this and why it is doing like this to us. So what we are going to do is we are going to look at the mechanism of these two reactions in order to understand the difference in the formation of products. A very important part of your syllabi, so please make sure that you write. Mechanisms. Look at what you got on your screen. Now what I have done over here is I have listed the mechanisms under two columns so that comparison becomes easy for us. So on the left hand side, it's the conversion of alcohol to an alkene, whereas the right side shows the mechanism for the conversion of alcohol to ether. The font is very small, right? Don't worry. So what I'm going to do is I'm going to make it easier for you to note down the mechanism for offline reference. So first I'm going to take up each of the mechanisms separately and then do a comparative study of the two. Now the step 1 of the conversion of alcohols to alkenes, we know that we are going to convert an alcohol to an alkene. That means our OH has to go. From our earlier study of nucleophilic substitution reactions, we know that OH is not a good leaving group. It's not happy to leave. It's too attached to the carbon because it is happy to share its lone pair of electrons over here. Right? So we need to first make it happy to leave. And how do we do that? We do that with the help of the proton. And where is that proton going to come from? It's going to come from the sulfuric acid or the acid that we've taken in the reaction mixture. Because we are specifically talking about acidic dehydration of alcohols. Right? So when our oxygen over here, full of lone pair of electrons, sees the positively charged proton over here, it cannot resist the temptation and it says, invites the protons like, come, I can share my electrons with you as well. And our proton is very, very happy to do that. So the proton leaves the HSO4 negative and immediately gets connected to the oxygen to its lone pairs. Now this intermediate which is formed, first of all there's going to be a fast process because oxygen is very good at tempting hydrogen, right? This intermediate which is formed has got a positive charge on the oxygen, so an oxonium ion. And specifically we are talking about ethanol or ethyl alcohol. So it's ethyl oxonium ion, which is nothing but an alcohol to which a proton has been added. See, this was our alcohol molecule. We've got an additional proton over here. So what have we formed? An oxonium ion. Now, do you think this is a very stable arrangement? Can it exist? No, it's not, right? So the next step of our mechanism is where what will happen is the water. Now, where's the water? Look at this, HOH. we know that oxygen is very happy to bond with hydrogen all the time. So what it does is it withdraws the electrons that it was sharing with carbon and says, I am happy to be a friend with these two hydrogen atoms and I am going to leave. Now, you see it is leaving with its bond. Now, when it is leaving with its bond, what will happen to the carbon? Yes, it is left with a shortage of electrons and gets a positive charge. It's an carbon with a cut on it, right? It's got detached with its electrons. So, carbon with a cut, a carbocation. Carbocation stability, do you remember? Yes, 3 degree, 2 degree, 1 degree. We did it in the previous video as well. Now comes the interesting bit. Either it can acquire some negative species, so probably it tries to attach itself, but it's not very happy to attach. So what it does is, it's very sad, and because it's positive and it's got a small structure, so what it says is, okay, HSO4 negative over here, the bisulfate. Yes, don't forget the bisulfate which had been deserted by the H positive. It says, okay, can I please get a hydrogen so that I can be more stable? So that is what happens over here, and the shift of electrons takes place and our carbocation changes into a stable alkene, and again this process is going to be a fast process. Notice that in each of these 3 steps we have drawn reversible arrows. Each of these is a reversible process, but the second step, being the slow step, is the rate determining step, right? Conversion of oxonium ion into the carbocation. Take your time, pause the video, note down the steps of the mechanism of this reaction. Let us now do the second mechanism, conversion of ethanol to ether, and that takes place at what temperature? Can you help me recall? Okay, 140 degrees Celsius. And what is it in Kelvin? It's nice to keep testing yourself, right? Okay. First step in this reaction is exactly the same that we saw in the previous mechanism. And what was that? The protonation of the alcohol by concentrated H2SO4. Wonderful. So that saves a lot of the explanation. And we've got an ethyl oxonium ion. When you have to represent this reaction, please don't forget the arrows to show the movement of the electrons. Hello, don't be lazy. Write the mechanism. It's good. It will help you. Okay, going on to the step 2. Now, this is where the difference comes in. So, what happens over here is, now the alcohol, which is protonated alcohol, I've just compiled. So, instead of writing it in this form, in the structural form, I've just condensed a part of the formula. So, CH3, CH2, and then now we've got this protonated alcohol. Here what happens is, because of the temperature conditions, reaction conditions, there is a 2 steps going to happen together. Now what are those 2 things that happen? Now here, like we said earlier, this water molecule is ready to leave because oxygen has made a happy home for itself with the 2 hydrogen atoms. So let's show that with the help of the arrow. So what has happened is oxygen withdraws its electrons. Now remember, our carbon here is going to get sad because its electrons have been removed. Okay, so who comes to the rescue of carbon? Yes, it's this alcohol molecule. And what does this alcohol molecule have? It has low lone pair of electrons on the oxygen. This oxygen says, never mind, this OH has left you, I am ready to share my electrons with you. And that is what it offers to the carbon. So what do we have? We've got a new structure wherein we've got, let's start from here, CH3, CH2. Okay, CH3, CH2. And the oxygen becomes attached to the carbon, CH2, CH3, CH2, CH3. And remember, oxygen had gone with the electrons. So we are still deficient in electrons, or we are actually proton rich. So this is actually my ether with an extra proton. Interestingly, this is a slow step. Slow step means a rate determining step. And rate determining means there are two molecules involved in this, two species which are involved. So bimolecular. And it involves a substitution. So it's a nucleophilic substitution reaction involving two molecules, hence SN2 reaction mechanism. See, there are two things happening simultaneously. First, water has become a good nucleophile. The OH has become a good leaving group. Sorry, not nucleophile. It's become a good leaving group. And second is another nucleophile, nucleus-loving species with extra electrons is coming to attach itself to the carbon. That is why it's nucleophilic substitution reaction. One nucleophile being replaced by the other nucleophile. Now we know that it is proton heavy. And who comes to the rescue again in order to help it rid of the H positive? Yes, don't forget the HSO4 negative, bisulfate negative. So what will happen here? Yes, the hydrogen says to oxygen, okay, you can keep this electron to yourself because I have got a friend in HSO4 negative. With the result, we get the final product as CH3, CH2, O, CH2, CH3. That's an ether. And again, our H2SO4 is regenerated. It's simply acting as a catalyst in this reaction. Now, let's have a complete look of the reaction mechanism that we've done. Yes, I'm sharing the screen so that you can take a screenshot so that it is easier for you when you have to use it as a reference material. Please don't forget to write these reaction mechanisms yourself with your own hand in order to get better command over the topic. Now we took the mechanism of taking especially the example of ethanol over here. Do you think secondary or tertiary alcohols will undergo similar mechanism in order to produce ethers? Actually, no. Because if you see, we are talking about a nucleophilic substitution reaction. Now, secondary and tertiary alcohols means the number of alkyl groups will be more. So because the number of alkyl groups are more, do you think they will, they're already loaded. So understand here that there would be a CH3 here, there'll be a CH3 over here, right? So it's already loaded with alkyl groups. Do you think it will entertain or it would like to have another molecule attaching itself to the carbon? No. Carbon can't take that much load also. So that is why what happens is in the case of secondary and tertiary alcohols, it is by default a dehydration that will happen instead of bimolecular nucleophilic substitution. That is why for both the mechanisms I've taken ethanol as an example. Right? I hope this clears all your doubts. And we will be ready to learn a very important reaction which we call as the iodoform reaction. I'm going to deal with it separately because it's a very important reaction. So that's going to happen in the next video. By the way, we still haven't done the physical properties. Stay happy, stay healthy, and enjoy your learning journey. See you in the next video.